Yeah. Okay. Cool. Computers actually work sometimes. It's great. That's our job. So hello, welcome to the latest Scratch workshop. Thank you again, Alejandro, for making AV systems happen. This time there isn't so much a DSA theme, so it's not like stature trees or whatever. They're always all connected. Instead, we have some real-life interview questions that people have encountered, sharing their experiences and so on. So I can start by describing one. I don't want to immediately throw people in front of the camera. But we can start with, we might call it like the largest lake problem. And for a bit of the behind-the-scenes stuff, it's because it's been a little crazy for me, so I'm not quite as prepared as I'd like to be. But I think it'll be fine. So the question is, we might represent a landscape or a map as a grid, zeros and ones. That's not quite interesting. And we might say, oh, yes, sorry, this is clear on the screen. And so, and you might imagine, like, I think on MS Paint, another sort of fun graphics program, there's sort of this, sometimes it's called flood fill, but this idea of like, these ones are barriers, and the zeros are sort of empty space. So you say, oh, I want to fill, you click here, and you say, I want to fill the empty space with color red. And so this is a much simpler version, where you say you have this grid, and just find the largest region that would be filled by that sort of paint. Is that actually the question? Oh, okay. Yes. All right. It's not. So in this case, it would be applying the eraser. In this case, it would be this region of 3. So there's 2 regions here. These are connected, and this is connected. So this is a region of size 3, and this is a region of size 1. And so the question, more concretely phrased, would be, we might represent this grid as a list of numbers. And when we promise it's not empty, we promise it's square. So there's nothing too crazy going on, like let's not worry about the input. So in Python, we might say that, size of largest lake. And I call it a lake, just that's not like the term mark or anything, that's just the one. And we get a map, M. And so to get a sense of this question, and so there's a few things we can explore with this question. Just to really start with the basics, what do you think our return value should look like? Like what are we, we're providing some API, we get a list of lists, and we spit out
I'm not sure exactly. I was thinking maybe we could return indices where the largest lake starts, but that's not very useful, I think. Like we kind of want to know where exactly it is, so we need a way to tell kind of the boundaries.
Yeah, so you're saying, how can we describe the largest lake? Like it's kind of tricky to say what to express that.
What's the largest? The lakes are the zeros?
Yeah, so in this case, you can imagine sort of, it's raining a lot or whatever, and where will the water congregate? The ones are hills, the high places, the zeros are low places, and here we assume, I guess it's, impassable outside. Here there's 3 of these zeros are connected, so they're, and here we don't consider the diagonal connection, so we say this is a separate lake. And this lake is size 3, and this lake is size 1. And so I sort of asked a leading question, I said, well, what should we return? And I tried to sort of subtly underlie the size, and not just, that's being a little fun, but it's a very common thing where it's like, oh, okay, well, I think reading a lot of these questions, there's the intuition where it's like we care about, of course, if we were trying to find the size of the largest lake, we'd probably care where it is. But the question's not asking for that. And it's just don't make your life perfect. So it's very, very general. And this was all like, it's not just interview questions. Like if someone says, hey, we need a tool that can help us do this, they might mean that very literally. Like, don't try to ask them if you should do something more. You don't need to read their minds. So in any case, so we're going to take a list of lists, and I'll be more explicit in a second, and return a number. So if we get a representation of this, we should return
3.
yes. So I know you introduced this question to me. Had you given it a shot, would you like to share your approach? Or
So it's
I don't.
it's
You're
actually-
welcome to share as much as you like.
Yes, thank you. It's been a long time since I attempted it, but it just stuck on my mind. I think what I tried was to find the first 0, basically, and then explore all the surrounding squares. And then for each one of those, explore the next surrounding squares without the ones that we had already explored. And then I don't remember how I kept count.
Right. So that's more than enough fuel for the discussion. Do you have any immediate reactions to this question?
I was
Have you seen this before?
No, I haven't seen that before. But yeah, when you said it doesn't matter where they are, like, I thought about just like looking for zeros. So,
Yeah, so we certainly, there's the question of how do we find sort of the starting point. And yeah, there's definitely like, okay, we want to find the largest, we want to find the size of each little lake. And we can start with 1. So we find the 0, we start with it, and then we start sort of exploring. So here it's like, okay, maybe we can sort of down to the right, but you can imagine maybe, in a different world, it kind of swoops back up. So how do we know to go up? And then if it's kind of a big empty one, it's like we might end up going in a circle. So there's sort of a lot of challenges. And this goes to, I love the analogy of vocabulary. And I hope to get us towards a point where we start saying, oh, of course, this is sort of mostly a new problem for us. It's not something that's generally covered. But we can start seeing analogies and kind of, it doesn't say, oh, now I know what the code, but it's like, oh, I can start breaking this problem down into things I've seen. So, I said something else that I wanted to address.
Like exploring all the adjacent ones, and
So, please.
exploring, finding the first 0, and then exploring all the squares around that 0. And then we see another 0, we move on to that one, and then repeat the same step, exploring all the surrounding.
Oh, it's just how to count.
And then, yeah, the problem is something I don't remember how I was trying to do.
Yeah.
Keep it account.
Yeah, so there's, on one hand, we don't need to remember the actual shape of it. On the other hand, we have to keep something about it so we don't double count or whatever.
oh, this reminds me of that game.
Like Minesweeper?
Minesweeper,
Oh,
yeah.
yeah. Yes. Actually, yeah, when you click it and kind of empties out a lot of space, it'll be a very similar enough idea. So let's pretend for a second that we're in hostile territory. We're asked this question: how do we start breaking? What's one of my favorite ways of breaking down how to approach this? You see it, you don't know what to do. What's something you can always do? That's a bad way of phrasing it.
I think cracking a code interview mentions this maybe as the first step, which is, oh, actually, I might be lying, but try to think about the simplest input that you could have.
Yes, I agree with that. So, what's the simplest input? And this is also where that's a little unfair because we don't really quite see what the input looks like in code. What do we, at human level, what do we think it looks like?
I think it's going to be an array with one element where that element is another array. And that inner array has only one element that is a 0.
Okay, so in Python, sort of most conventional human syntax, we write an array like this, right?
Mm-hmm.
This shouldn't be making errors. Hello. So we write an array of numbers like 2, right? And an array of arrays, talking with other people, I have some intuition, sometimes they're kind of overwhelming. But really, instead of 1, 2, 3, it's just a little array, and so on. And these, of course, we have. So it's hard to really wrap your head around it sometimes. Like there are complications, but like is this? Well, I should separate this. But like, are we comfortable enough with the idea? Like, how might you print out this 2? For instance, we have an array A. So this. How do we print this 2 out?
A bracket. Whatever that first array is made.
So what's the first element of an array? How do we get to that?
0.
All right, so A0 is this.
Yeah.
And we want to get a 2. So how do we get that?
Brackets again, and then index 1.
All right. We passed the first. So yeah, it's sort of intuitive, right? Notice. Yes. Glad you guys get it.
I would have said A bracket 0 bracket 1.
Yeah. Oh, is that what I? Or,
No, you did it right. I was
no, that's right. That's right.
No, you did it right.
This is recorded for posterity. So let's make sure. If this is the start of the array, A0 is this first element, and then 1 is the second, 1's.
Yeah.
Okay.
That's right.
I'll check the recording later. Change
I would have
history.
been at the compiler, like, why is it this way?
So the simplest input would be S. So this is going to be an array, like this. So, and like just in my little map drawing, that should just look like this. Cool. And I agree that this is the smallest one. And what's the answer?
1.
Okay. What's another simple one that would be a nice test case? Oh, 1.
Zero.
Oh, okay. Being legalistic. 1. What's the answer to that?
0.
And what's perhaps like and this will be more subjective, but like a simple but also interesting case. There's a few, but what are some of the things that kind of make this problem hard and interesting?
0, 1.
So something like that.
Oh, well, that's the thing. 0, 0.
All right, so like bigger 1, 1, 0. So what's the answer to this one?
1.
Or, and in fact, I would say an interesting one is this. So now it's like, okay, we better recognize that these are connected. And we don't even have to go to 2 dimensions for a while. We can do this. What's the answer to this one?
1.
Uh-oh.
Oh, 1.
No.
Because they're not connected.
Yeah.
And I wrote up a couple, and let me just, not that this is super duper, but as the last one, we can have the computer can come to me. 0, 1, 0, 1, 0, 0, 0, 0, 1. So what's the answer? This will make it a little harder to read, but 0.
3. 4.
5.
Yeah, that's a little scratchy, but 1, 2, 3, 4. Okay, so we certainly so there's a limit to this technique. I don't think we see what algorithm to implement yet.
Yeah.
So one thing that I do want to pound in is like a vocabulary idea, because we've seen a few questions with grids before, have we?
Yeah.
And what's a nice way of breaking down a grid in an algorithmic sense, not like a data structure, or like not in an explicit representation in code, but what's a nice way of thinking about grids?
I'm lost.
Yeah, these are sort of open-ended questions. So one thing I'll kind of illustrate is that we care. This is 3 because this node is connected, or this square is connected to this square, right? And this square is connected to this square. But kind of intuitively, on this diagram, this square is not connected to this square. It is connected, this square neighbors this one, and it neighbors this one, but it's not really allowed to be connected to them.
How come?
I mean this in the sense of like, the way the question is saying, we want to find the largest link. And build links, right?
Yeah, okay.
So of course the kind of the human analogy is like you're filling something up. You know, like a train or there's potholes or whatever. But I guess a more computery way of thinking about it is that, you know, where are there connections and where are there not? There's some forgotten memory.
The fact that you said no and then you corrected yourself.
Yeah, exactly.
A good way to think of grids is graphs. Yeah. I'm not sure we could go more specific on acyclic directional.
Oh, well, let's not get ahead of ourselves.
Just graph.
Yeah, so to try to bring it home a little bit. So yes, I absolutely agree that a graph is sort of, it's still not giving us the answer, but this is sort of, you know, one of the first keys. We're like, hey, this seems, it might be wrong. In this case, I think it's right, but it might be wrong to think of this as a graph. It's worth exploring. So we're thinking, oh, okay, if this were a graph, we might say, well, each square should be, confusingly, I would go a circle, or, you know, these are zeros. And now we have 9 nodes, because, and, you know, this is something, we're not even at code, but this is, conceptually, we're building a graph. And, hey, and so graphs are at the simplest level. There are these nodes which represent things, and edges which represent the related, that two things have a relationship. And that's very open-ended, and that's why graphs are so useful, because you can sort of shoehorn that into a lot of situations. So here, we want to find which squares are connected. Or that seems very useful. So I'm already thinking at one step and saying, well, I'm going to make a node for each square. But I haven't drawn any edges. What do we think? What might be some useful relationships to keep in mind?
They have to be equal.
So, like, if 1 and 1 are equal, we draw an edge between them?
Oh, no.
No. Okay.
I think that one makes sense.
If they're equal to 0, then you draw an edge.
So, I'm going to be annoying, but I'm going to be a computer and take you literally, saying, this node represents this one, and it's 0. This node represents this one, and it's 0. So they're equal. So I'll draw an edge. Is that what you were hoping for? Yes. I wasn't looking. And I mean, this is like a skill, or this thing to practice with graphs. Like, how do you?
How about we just connect all? Like we say, like first node has the next, which is I don't know, either up or down, whichever way. And then you check.
Write it up or write it down?
No, sorry, down or to the right.
All right. So it's only, I have to choose one of them?
Yeah, because then if you're gonna check if what's in that node is equal to the previous node, the headed.
So you're thinking of sort of building edges out. You're saying,
yeah.
Here's this, let's sort of put feelers out and say, which one should I be connected to? So I'm connected. So I try this one. I don't know. This is a 1. Mine's 0. Okay, and then we instead draw an edge here.
And then you do this.
Or, I mean, is that what you're saying?
Yeah, but I don't know if that's gonna work all the way, but at least we'll get you to the second.
Okay.
Yeah, I think that sounds good. Like that will be like trying to check before we actually say this edge exists, or this connection is allowed.
Yeah, so this is definitely a nice approach, and we will definitely be using a tool like this, or I use a tool like this in some. I do want to stress it's annoyingly slow, but sorry, I guess. All right, I do. We're now more human. Sorry. Oh, are we muted? No. Okay. Sorry, it's all. Oh, the UI is always different. So sorry, I got to check. Yeah, so we're thinking in a sort of like execution way, like here are the steps we're going to do. We're like, okay, we can take this, we have these nodes, they're now created, and now let's start running code to add edges. It's hard, like it is hard, but I would suggest to resist that temptation. That we still get to kind of in humanish terms, no code, get to just define that here are the edges that we want to exist. We still have to act as if they do and so on. But you don't feel constrained by what you can implement or what you can see in infographics. Well, like, of course we can implement what you're describing. But what I mean is, like, okay, we're talking about this mechanical process where let's try this one, and then if that doesn't work, let's try another one.
Okay.
Can we phrase things, you know?
So,
If I thought this struck you.
well then, what if we just connect everything and then go erasing edges and done?
What if we connect? It's like, I guess I'm trying to jump to what you were describing, Aaron, as to like the implementation. Because I'm thinking, we just know that we can connect the left topmost node with the one right underneath it. But I guess like I'm asking myself, how are we going to do that? But if I understood what you're saying, it's like, don't think about how you're going to do that connection yet. Just
Yeah. I think so.
okay.
Where there's this idea of like, well, let's add all the edges and remove the ones we don't want. That's like still a little algorithmic and still a little execution focused.
Okay.
So it's like, I guess phrasing it another way, what would be a really nice graph to have? What would be something you'd like to have? Wow, the graph is complex.
Where it's just zeros, like a graph
Or-
that's like pure.
Okay, so that would be the simplest input. But let's say we have this nice complicated input, and we want a graph that helps tell us something useful about this input.
Oh, maybe a graph that it's only pointing to a node that is only pointing to another node, which is guaranteed to be of the same kind, or in this case, zeros.
So a node that is only pointing.
Mhm.
So I'm in the computer again, like one node that's pointing to another node.
Yes. But I guess I'm jumping ahead as well, saying a node that is linked to another node of the same kind.
Well, okay, so if someone says, hey, help me solve this problem, and I say, don't worry, here's this graph. Does this say much about this input?
No.
So, and I mean, like this is, I know I'm asking an annoying question, but like this is how we can, I'm trying to help you guys build sort of a vocabulary of like, here's how we can translate our problem to a graph. And that is, there's this enormous temptation to like, let's program something. Let's fight against it. Or, you know, trying to.
So could we just have like the first node have children, and then its children have children?
So a graph, you can have nodes connected in many ways. That's sort of that's what makes them different from trees, for instance. Where you can have a direction, and maybe we need that, or you could have, either it's considered both ways, or equivalently, like, well, you don't care about the direction, so this is usually called unpaired.
Got it.
So I will
Oh, yeah, so.
I really want to empower you guys to feel that when you say, okay, let's represent this input as a graph. You can make it whatever graph you like. So I'm going to take charge and say, I'm going to make a graph where, the nodes are sort of correspond. So this one corresponds to this square, this one corresponds to this square.
Yeah, so,
And I'm only going to add, and I want the graph to only have edges when there are zeros that are equal to each other. So I'm only going to add edges between nodes that have zeros. Okay. Does that seem crazy? Does this seem useful?
yeah.
Maybe. Okay, I think it is. And you're all saying yes because I asked you.
No, but but you can do that? Like, you can just say, make an edge if it's equal to 0?
So, you can, because we just did. I know that's a little annoying. Can we do that? Like, and we say that to an interviewer, and we say, yes, I'm done with the question. So we're not done with the question. But the way to, if you open up Wikipedia or whatever and you start saying, I want to learn more about graph algorithms, and you want to use them, especially in a interview context, or they come up in real life a lot, actually. You need to have this sort of, you need to do this thing of saying, I just want there to be a new graph.
Okay.
And then you still have to make it happen. But I think, especially when you're like, let's learn to code as much as possible, there's that temptation of like, let's code the graph. Don't code it, just first define it, and then we can have code, and we can be very, very creative in how we actually represent the graph. So we might be tempted to have, I think I've talked all 100 of those before, or I forget who's been here for which materials. But you might be tempted to say, okay, let's very explicitly make a class node that has, what language are you going to Okay, so we have I'm kind of make this up, like something like var, int, or var x, that's like an int or whatever.
Yeah.
So that's 0 or 1, and then a list of nodes, neighbors.
Next.
Well, so in a linked list, you have a next, right? Because there's the next one. If I have a graph that looks like this, and I get this node, which is my next?
Oh, so got it.
So a graph, you can imagine, in a sense, it's generalized where instead of one next, you have a list of nexts.
Okay.
And you don't particularly care which one you like. They have to be in some order, just because there's an order. But it's not the first one's more important than the next, right?
Okay, got it.
And you can get very interesting things because, this one's next list is this node and this node, and this node's next list is this node and this node. And so if you aren't careful, you go back and forth a lot if you keep on following next.
Got it.
But let's say, for instance, so we have a graph. So we have this graph, and it seems useful. And we have, and we will continue to always build our vocabulary of graph algorithms and techniques and so on. And again, still, we're still in the design phase of this. What might we, if we could write a program that very intelligently navigated this graph, what might we want it to do? Like just in English terms, kind of what do we want to do? Okay, we got here to a graph. I'm saying the graph is helpful.
I thought we should traverse it.
I love traversing graphs.
We can only traverse through the edges, I think. Actually, we could traverse in other ways without, but for this problem we want to go where the edges stay fast.
But I have a question because if there's going to be edges when the nodes are equal to 0, why wouldn't that middle node connect to the one in the bottom right? Because it's equal to 0.
They're saying, well, this is also 0.
Yeah.
And so we should do this.
Mm-hmm.
So I guess that's a fair question. I was speaking too briefly when I was describing the graph, or really, like, it sounds sort of unfair almost. I want the graph to represent the thing, my goal in designing the graph is to, our goal is to have it represent useful information about this grid. And we want to find the largest link. And these cells are connected when they are neighboring, on 4 directions.
Okay.
But just the interviewer told us that they're not connected if they're on the diagonal. So I'm saying, okay, I care about 0 cells that are connected. They're connected according to the grid.
Okay.
So if they're connected to the grid, I'll add an in. And even though this is a 0, this is a 0, they're not connected on the grid. And so, kind of going the other way, I'm not connecting this one and this one because this is a 1, this is a 0. So that's sort of the other implicit thing. And that's also in a similar way, that's why I didn't draw a line here. Because even though these are both 0, in a grid they're on a diagonal, so they're not connected down. But yeah, so we have this graph, and I asked what can we do with it? And all numbers, well, we can traverse it, which is sort of like, in a good way, that's like almost always the right answer. As in, we care about the structure, like, in a very abstract sense, we care about the structure of this thing. This graph kind of describes that structure. And let's explore that structure. That's just vaguely motivating. So if, for instance, we're here, we can go for the edges. And there's some intuition where it's like, oh, we can sort of explore this, and in exploring it, hopefully realize the size is 3. So if I can do a graph, so now forgetting this one for a second, this is vocabulary. I give you a graph and I say, let's traverse all the nodes according to how they're connected.
According to how
Like as in, let's not, so for instance, we might have a class graph that has, an upper class node, which has, the values of this is in Swiftish, since it has the value that's an int, and, neighbors, yeah, I wrote down here, neighbors, that's, a list of nodes, and maybe the graph, this is really a node reference, references in Swift, is that the thing? Okay. These are references. And it just has nodes. Or just say V N lowercase n for the list of nodes. I'm being a little free with syntax. Like a graph is just a list of nodes. Each node is sure has a value or not, and it has links to other nodes. And we're assuming it makes sense. The nodes are there. So if I say let's traverse all the nodes, we could just do a for loop for this list. But that's usually not what we want to do with a graph. Not ultimately. What's a classic way, and this is more of a vocabulary, but so it doesn't hit you, don't take you out of it. What's a classic way of exploring a graph?
So we do the algorithms like breadth first search or breadth first traversal, where we visit all the neighbors first, and then all the neighbors of the neighbors.
Yes. No, don't worry about the implementation of it yet. But yes, breadth first search is a great one. What's its trend? What's its counterpart?
Breadth first
Yes.
search.
Does that ring a bell? Or is this?
I've heard it before, but I don't think I've used it.
For a while, I did more like one-on-one stuff, like interview questions. So, what are you interested in? Everyone was a preference search separate. So, and I keep overloading the word vocabulary. But yes, so what? I like to draw connections, so I'm trying to think about it. Roughly, like, when you were describing this question to me, and there are many similar questions like this. Like first, like, and this doesn't mean, oh, it's the answer, but like, oh, I was familiar with, hey, we can represent this grid as a graph. And we can add these edges that express kind of this nice structure. Because we want to find the largest things that are connected. So let's add edges, let's connect them in the graph, according to the grid. And then we want to find the size. Finding the size is exploring the whole connected chunk. And we can do that with depth first search or breadth first search. And I'm saying all this to illustrate that it takes a while to get comfortable with this stuff. But that's sort of, if you can see the problem and say, oh, I can solve this with depth first search, that's 90% of the way there. You have to implement it as well. But seeing that insight is sort of, once you get to that point, like, okay, then you can debug it. You have to get roughly the right code. But that's something we can take away with some of the more general techniques of breaking down a question. And it's hard to kind of have all this in your working memory when you're in an interview setting. That's why we practice it here. So now that I've said, okay, we have a graph, these connected nodes, and let's just say we have depth first search. So we're still not writing code yet, but we don't say. How might we, in a high level description, what sort of, do we see an element?
We'll be using breadth first.
Well, I say depth. Depth is easier to say than breadth. They're both kind of hard to say, and I say depth first search.
Could you repeat the question?
Oh, as in, so I'm slowly sort of trying to provide motivation for like, okay, breaking the graph, we can use one of these depth first search, breadth first search algorithms. Is that enough to take us over the finish line? Do we think we can sort of describe how to solve this problem?
Yeah.
Does that mean you would like to try to describe how to solve the problem?
Okay, so we created the graph,
Mm-hmm.
and we're saying, oh, we're going to use breadth first search or depth first search. So then what we'll do is we'll keep a counter for each node that we find. And then I return the counter. I don't know.
All right, so yes, it's good that we're remembering we still have to count stuff.
Yeah.
So how?
I guess I know that depth first search is most of the times implemented recursively.
Mm-hmm.
And we want to keep track of count. With the recursion, I'm inclined to think that we need minimization. Or kind of pass the count down.
Okay, so now you're thinking, okay, there's this intuition of we're using depth first search to explore this connected region, and while we're exploring it, we want to count. We want to keep track of it. Don't overthink it. Memorization is cool, but we don't need it. That is cool. Let's not extract that way. I think an analogy that others have found useful as well myself is like depth first search and breadth first search both serve the same purpose, but you can imagine it being, it's like a for loop over connected nodes. So you see them in a certain order, of course, but you can imagine that, hey, we're iterating over all the nodes that are sort of reachable from each other from the starting point. So kind of, that's sort of the high level. So you can imagine, like, it's not written that way, but you can imagine something like for, node in depth first search of some starting node. So like for each node, out of all the nodes that we depth first search explore view, so the first one might be, if we do print n. That's my go-to example, where like, if this node was named 0, 0, and this node was 1, 0, and this one was 1, 1. Sorry, I introduced you to working. But like,
I think that makes sense.
okay. Then this might print out 0, 0, and then 0, or 1, 0, and then 0, 1. Or 1, 1. So like, that's just to provide this idea of, okay, we haven't implemented DFS yet, but we can use that to iterate over all the nodes that are connected.
Okay.
So if we can iterate over all the nodes that are connected, do you think we can count how many we have iterated over?
Yes.
And how might we do that?
And in here, just to make sure, so like if we have a loop that looks like this, we're guaranteed that the depth first search is only going to give us nodes that are connected. Then we can just keep a counter that will be increased in the body of this for loop. And we know that like as many times as this for loop, the body of this for loop runs, that's the number of nodes that are connected, or the size of the largest lake.
Yeah.
Okay. I guess like,
And so syntactically, we all have something like this, but conceptually, we will. So again, we won't write code else.
that's really interesting. I really like that you're giving us like these kind of hints, because it stretches our minds.
Oh, maybe. Don't say that until you solve a problem in the wild from this.
Okay.
Results driven. I'm glad it seems you were right. And so if now let's pretend let's return C. So here's this little module. And we can imagine wrapping this up in a helper function. Right, size from node, not forget its name, but so we can give it a node U. And it will return all the nodes that can be reached from the node U. So this is very much pseudocode, it's not correct. Or it's not executable. But let's pretend we have this. Do you think we can solve this problem now? Or is the finish line in sight? Or closer?
Yes, I think it is.
Well, so you have an idea how we could apply this?
So I'll just apply I guess I will need to keep kind of track of what's the longest or the largest. But if we can call this function on every node in the graph, then by the end we will have the answer if we keep track of what's the largest.
Yes, so for each possible node, S is size from node and I'm taking what you've suggested and I'm running. So here there's this idea that okay, we want to iterate over all the nodes, but whereas DFS or DFS we care about the connections between those nodes, here this is just all nodes. And we don't care if they're connected or not. And then we say, well, what are all the ones we can reach in this particular node? Let's remember it's the biggest one. This is a pretty common pattern. You have a max that or you have some n that's always equal to the max of itself and some newly computed value. That's how you find it. biggest thing. That comes up often.
I think I'm confused about this depth and breadth. It's like, so within a graph, does it have children? Can it have children? Is it just neighbors? Is it always gonna be a square?
I will fill in, or we can fill in the DFS stuff in a moment. I just want to, we're almost done with the outline, so I just want to bring that up.
Oh, okay.
The only this is more of a debugging thing. The last thing is if, n dot value is 1 and continue. And that's just to capture the idea we, and in fact, really, we probably simply shouldn't have had nodes to begin with from the lines. We should have simply represented our grid like this. But if we represent each one as just a node of no neighbors, sure, but that's, we want to return 0 in this case. As being a little pedantic, but we should have represented it like that. Oops. But what I want to, so we're about to get to the implementation stuff. We're talking about graphs and DFS. But I want to just stress that, this is, it depends on your actual interviewer. But I feel that this is a pretty good, if you can get to this point, I feel you have demonstrated that you can take the problem, translate it into a sort of a fairly well-known concept of graphs, and then use fairly sort of standard techniques to get the answer you want. And so even though we haven't written any legal code yet, I feel we made pretty good progress. I'm a little biased.
I feel like something that or at least I do, is I get worried at the implementation and I'm able to move to the next block.
Yes.
So I all should help me.
Yeah, I definitely understand the whole I'm about to commit to something that I don't know how to implement. I feel I would hope that obviously we can always get more familiar with DFS and DFS stuff. But if you get to a point where you say, I know that this is the thing that will help me navigate this. I think just having that sort of, I always go back to that analogy of vocabulary. You kind of know what this word means. You know what DFS is and how it can help you. And I see that as the way forward to more so if you implement it 10 times, maybe that's the right way to get that comfort. But bugs are bad. But knowing demonstrating that you know how to break down the problems, I think the more interesting. So are we ready to? If we need a moment to recover, to reflect, and we can talk about the actual implementation.
Yeah.
So I need to study that for search.
We're gonna implement it here.
Perhaps.
Yeah, so how well will we implement it is a question that I can ask myself. So first of all, a bit of what's the term? Metagaming, thinking outside of the scope of the question. Graphs are generally considered a little bit more advanced than other data structures. On the other hand, some encountered reliable, so that's why we're going over it. So they are trickier, and I think a lot of it is because they're sort of so open-ended. And because I want to get to the other question.
Oh, and it's also a graph, so I need a grid, so.
All right, that's perfect. Wonderful, it's all part of the plan. I'm going to sort of, I've mentioned this a few times now, but I think an idea that is one of the more difficult hurdles, and one that's a lot of, you can go to Wikipedia, you can type in that for search. and like it'll be hard, but like that's something that, you know, with enough persistence, I think we get. One of the things that I think is much harder to convey from like text, like what I know, is like the weirder stuff. And I'll show what I mean in a second. So I'm going to erase the input examples. Where, whenever we've talked about data structure, I'm assuming whenever you talk about data structure, you talk like, you know, let's talk about linked lists. We have, you know, a node, you know, sort of like what I did with the graph here. A node has a node next, and you know, an int value, and you know, when someone on the board says here's a linked list, you say yes. You know, this is the node, this is the next arrow, here's the map, like it's very sort of explicit.
Mm-hmm.
But a lot of times, data structures are more implicit. I don't know a better word. And what do I mean by that? What I mean is I'm not going to make a node class. I'm not going to have edges, I'm not going to have neighbors. Streams of shock and astonishment fill the room. But let's see, okay, it's only 30-ish lines. Oh, 30 lines. I think it works. Let me just. So, if we have this, let me just reproduce that here. If we want to find size of artist lake, I have a list of this. Let me do this. Okay. I'm going to draw stuff and I'm going to write real valid Python that I ran, and it works for at least my custom codes. I'm going to say, so I'm not going to try to adjust the variable names because that'll just be confusing. I have size equals 0. It's the size that's, you know, it's a good default value in this case because nothing can be smaller than 0, and 0 is the legal answer. And then I have for I in range. Yes, instead of m, I have range of the length of the length. This is just the Python way of saying for I from 0 to the length of this. So this is just from I from 0 to land.len or whatever. And then for j in range len of land sub I. And again, this is just j from 0 to the length of the ith row.
Mm-hmm.
You can also maybe just do length 0 as a size division. This is like I promised that the input's a square and all that, or a rectangle and all that crap stuff. So equals land I sub j. So hey, we know what that is. And then if cell equals 1, continue. Otherwise, size is the max of, you all know what continue is, right? That's I gotta rephrase it.
Sorry?
Is continue new? No, you all know. So size dfx size, telling helper function name, land I j. And then this ends, return size. Obviously, this seems important, and we haven't implemented it. But honest to goodness, that's the Python code I wrote. And you see how these two for loops seem pretty similar in spirit to this one. Here we're saying for every node in the graph, and again, let me add 1, 1, 1, 1, 1, 0, 0. That's not really legible, sorry. But for every node, you know, compute the DFS from that node or the size of the DFS from that node, and you know, figure out if it was bigger, if it's the biggest one we've ever seen, and then ultimately return. Here, well, there's no nodes, we're just going over indices. But, you know, like we were talking about how this node should represent this cell. So I'm just saying, oh, I'm lazy. Rather than making a node, I'm just going to talk about the cell. And in my head, I'll keep track of sort of the analogy that I have. Do you guys doubt me? What? tried to find like a better, because if you're in front of a room and you're saying, any questions? Everyone's just silent. So I tried to phrase it differently, but now it just sounds more challenging. Like, fight me. Disagree with me.
All has our mind.
But, as in, like, if something seems suspicious or whatever, but, like, I hope this is sort of empowering. We're like, oh, I don't need to actually implement it. I can just write code. Not sure if that's really the right way. Here we are. So I'm going to now implement DFS. Def DFS is. So that's this. And it takes land I and J. I'm going to have to write a little smaller here. Where C is a set, like the past tense of C. Work list, so I'm going to have to break out, or for brevity, I broke out a little Python stuff. Are you all familiar with the term tuple? It's behind the scenes, it's no different from like a class or a struct. But it's sort of a concise way of saying, hey, I want to make some kind of type and it has some fields. So Python just uses parentheses and commas. So this is basically a struct of two integers, I and j. So it's just the syntactic way of it. So this is so what's the length of word list right here?
1.
Do we have a quorum? We have a skeptic. So in this case, it's 1 because this tuple has 2 elements, but it's 1 tuple. Just like how if you have an array of arrays,
Could we represent tuples as just an array with 2 elements?
Yeah.
The same way?
Yeah.
Okay.
So yeah, that's an easier way of imagining. But like so, this array, even if these have a million elements, and this array has 3 elements, just this distance. When you call array.len, you'll get 3. So this similarly works just as well. Just trying to preempt any confusion. While work list. Right, that's all. Actually, that's all you need to write. I'll be a little bit more explicit. So while the work list is not empty, so while there's something in it. So right, its length is 1, so it's not empty. So this will at least run once, which is important. A B equals work list dot pop. So pop stacks, right?
Or Q.
Okay, yes, it's better.
Arrays.
Hold on. In like the data structure world, you wouldn't really say pop. Like pop does imply that you're doing some sort of queue or stack. But yeah, so here, right, when you start with IJ, this is saying, get me the first or last, whatever, tuple, take that out of the list, and set the A to that I and B to that J, right? Yeah. And obviously, as might be implied, we'll be adding things to the work list, and then we'll be popping those in a later iteration. So if A, B, honestly, this is what is in scene, continue. So we have it. So scene is a set, and it's an empty set right now. So, this loop will iterate multiple times. And in fact, scene will add A, B. So if we haven't seen it, or if we have seen it, great. But if we haven't seen it, let's immediately record that we have it. And also, oh no, there's another function I forgot. Okay, don't worry. For x, y, in neighbors, where's this? Land A, B. If land x, y equals 1, continue. Almost there. Work list n x, y. Got it. So this is what we'll do. This one here. Return the size of what we've seen.
So you can add a tuple to the set.
Yeah, so here, you know, for brevity, I had to use a bit of more fun features. But yeah, so this is a, you can imagine this is a set of tuples. Right now it has no elements in it. And then we will ultimately add, when we go through the work list, you say, okay, let's take the next thing that we see on the work list, or the next thing we have on the work list. If we've seen it before, we've already done it, that's not fun. If we haven't, okay, we've seen it now. And before we're done, we'll say, let's look at all the neighbors of this node. So now, oh, this is a tuple, it's an I and a J. But just how, like I was saying, well, we can check, you know, if land ij is one, we can check this, and we're using this entry in this matrix as an analogy for this node. We don't even need the matrix anymore, or the array of arrays anymore. We can just say, well, here's the indices that we would use. So this really is a node. This ij, along with, you know, the graph, the array that they refer to, is enough to say this describes this node in the graph. So we still haven't allocated any nodes. There's no neighbors listed, but we're somehow able to think about this ij represents that node in that graph in our head. Going way back, that's why I was saying let's not worry about actually how to build the graph. Let's just describe the graph more. There's sort of an implicit build. Okay. I'm going to erase a bit of this. Neighbors is nice and quick. I have to use probably two fancy iterator. Is there a yield keyword in your languages?
What is it?
I'll tell you about it later. I just want to. It is. It's a nice convenience. It's not super duper. So the last function we use is def neighbors and I, J. So really, you know, we talk about usually the neighbors on a node. Here, again, just harping on. Here we don't have a node. We have the array of arrays and basically index it to that base. But you know, we just write our code so that everything behaves as if we have that. And we do have that graph. Very, you know, weird. And it's just this, an empty list. And then we just have to check a lot of indices. If I plus 1 is less than the length of land, so sort of conversely, if so if I plus 1 is less than length, we add this pair. And really I plus 1 and j, you can imagine this is I and j, I plus 1 and j is this node. And why do we check this? Because we don't want to do this. Just an array. And then there will be 4 of these, and it's exactly, I mean, we need to see this many times to get the intuition, but it's exactly what the intuition would suggest. So in a similar way, if j plus 1 is less than land of, you know, land, so I, ooh, that's, and then, you know, this is where typos come in. This is where you say, oh yes, it's a nice and minus. And you put the wrong letter somewhere. In a similar way, if I minus 1 is greater than or equal to 0, and I'll append I minus 1, j, if j minus 1 is greater than or equal to, so again, it's out of bounds on the other, and append I, j minus 1, turn n. And that's it. This solves the problem. And anyway, modular typos, bugs, it's honest to goodness, is valid Python. That's all.
And for this function, I think I'm not very clear on
Sorry, I just.
I think I'm not very clear on the neighbors function. Like for instance, if we had the I and J were 1 and 1, which is the one in the middle, this function will return an array containing the indices of the neighbors,
Yes.
which will be all the surrounding ones.
Yes.
Like,
That's true. So you're saying, well, hold on, there's no out of bounds concern, so it'll return this, and this.
okay, I was kind of thinking it will still do the corners, like the,
Oh, I
but
guess.
he's not gonna do those.
No, if you wrote like a for loop where like from I to -1 to 1 or whatever, 2 and J, like, yeah, then you get all 9, but here's the annoying thing, there's 4 calls to append. So we're only gonna add 4 of these.
That makes sense.
And I guess I was anticipating the other question, well, hold on, we don't want to treat this as a neighbor. Why are we?
Because it's not the same kind?
Yeah, and so then I say, oh, well, we dealt with that case here.
Okay.
So this, I hope not, but I would expect that this might seem a little sort of arbitrary, where it's like, I'm up at the front, I'm saying it works, therefore it works. But this is one, I think, of many examples you will find in your life of programming, where we can talk about a data structure, in this case a graph, even though there's no graph, there's no, class G, an instance of class graph, has nodes, this and that kind of thing. But instead, the closest thing we have are these pairs of indices into this array of arrays. But we just write code that interprets it as a graph. So here we say this is sort of the grid where we're looking up, north, south, east, west. Here, if I was really good about this, I'd have this over here. It's like this is not quite the neighbors that we want. But instead we skip the ones we shouldn't have added, and then by workless unappend, you're saying, oh, let's add the neighbors. Let's add the neighbors that are also 0. And that gives us the effect of having a graph with edges like this. And then, so I call this DFS, it might be DFS. It might be a little bit less efficient than it should be. But this idea of, so you may recall from earlier workshops, set, if you add the same thing to it multiple times, or, well, we won't in this case. Here we just make sure the set is where we remember what we've seen before. So we only add new things. And just if you believe me, this DFS thing will exactly, ultimately kind of flood out from a single node. And so everything that's connected to it in the way that we want will end up in this scene set, which we then compute the size of. So this is the interesting part, it's in this. I hope this was a little mind-blowing.
Yeah.
It was.
I think, and so if you go to like Wikipedia or whatever, and you Google, or go to Wikipedia and Google, DFS implementation, you'll often have kind of like, in the code where you really do have an explicit graph class and a neighbors method that returns instances of node objects, and that's easier to get a hold of. But not all graphs are so explicit.
Would you say that like a class graph and a class node will be object-oriented programming, and then this something else? Or at least not object-oriented?
I don't think that distinction helps here, I guess. Okay. So I'm not saying this is or isn't. I guess it's more like, I suppose this might be slightly more amenable to a functional approach, but no. Wait, that's illuminating.
You would say that the graph, a class graph and a class node thus resembles more of a object-oriented problem. since you're creating like these objects?
Sure. I guess like, I'm hesitating, because it's like, all right, yes it is, and it's like, what can we do with that information? I'm not really sure.
Yes.
What, as in like, I understand people say object oriented, and this is, and this isn't, and I've used some more examples. I'm not sure. That's usually from a more like bigger, like these algorithm questions are kind of self-contained. I just feel that it doesn't provide a useful analogy to like industrial work. So I'm a little over. We can leave time for another question.
Do you think you could share the input for this algorithm? I guess.
Oh, sorry. It's what we were writing.
Okay.
Like this would be fine. I remind me and I paste it to the side.
Yeah, I don't think it's hard to type.
But last thing, and I guess a question people are often annoyed by is how do you make this code more efficient? I want to, because you'll be so excited you'll be doing this at home for fun, and you want to enhance it. I'll point out one thing, which is that we're calling DFS size of every node in our graph, right? Or for every 0 in our graph. So in this example, what we do is we'd say, here, let's compute DFS. And we go, 3, great. Skip it, and skip it. We go, oh, let's compute DFS on this graph. Ooh, we do it again, and we still get 3. Well, let's compute DFS on this graph, on this node. Oh, we got 3. Some of that wasn't very useful. So for DFS, we do want to keep track of what we see. But this sort of suggests maybe we want to really keep track of what we've seen between all the different DFS indications. This is, homework to meditate on. But that's just, I'm sure there's other things we can do to make it more efficient, but that's sort of just probably the most egregious fault in this implementation. This is correct as far as like can tell, but there's a lot of room for improvement. So are we content with this question? Does it leave us with more questions than answers? Yeah. Yeah, I mean, graphs are tricky because they're sort of they invite a lot of these sort of more conceptual things. I mean, they're hard enough when you actually have an explicit object to latch on. So I'm going to erase this, and then are we ready to present another question? Oh,
Well,
don't jump
you
at
guys
it.
are gonna have to help out because I was gonna work on it. I've been reading it over and over, and I'm like,
Well,
this
sometimes.
seems very helpful, what we just did. I think that we might be able to come up with the answer, the solution really quickly.
With this problem, did you try to like attempt or like?
No, because I had a different one that I had worked on, but it was on my other computer.
Okay.
So then I had this one that I was gonna work on, so I'm like, yeah, I'll just go with this one then.
Yeah.
All right, so this one is called number of paths, and it's also a grid. And I'm not sure how you're gonna be able to see this, but you see that there? So the question says you're testing a new driverless car that is located at the southwest bottom left corner of an N by N grid. The car is supposed to get to the opposite northeast top right corner of the grid. Given N, the size of the grid's axes, write a function num of paths to destination that returns the number of the possible paths the driverless car can take. So the grid looks not like that.
We need, what are they, grips? The ones who move the camera? I guess can.
so the car starts down here at 0, 0, and then the destination is up here at. Wait, is that what it says?
Mhm.
Oh no, wait. The destination says 4, 4. So it would be like over here. Then it says, for convenience, let's represent every square in the grid as a pair ij. It's like, right, like you were doing earlier. The first coordinate in the pair denotes the east to west axis, and the second coordinate denotes the south to north axis. The initial state of the car is 0, 0, and the destination is n minus 1, n minus 1. The car must abide by the following 2 rules. Cannot cross the diagonal border. There's a border that goes. Did I draw this wrong?
That's fine.
No,
I think I drew it wrong.
so,
1, 2, 3, 4. Oh, wait, I'm missing one.
Oh, I see.
I'm like, why is this being weird? Okay. So the car cannot go on any of this. Oh, and since n is equal to 5 because that's the grid size, destination is gonna be n minus 1. What else? Okay, so in other words, in every step, the position ij needs to maintain I is greater than or equal to j. See the illustration above? For n is equal to 5. In every step, it may go 1 square north or 1 square east, but not both. If the car is at 3, 1, it may go to 3, 2 or 4, 1. Okay. So, the rules, one of the rules was that it can only move one. It can only move, oh wait, so we have I and we have J. And it can only move either I plus 1 or J plus 1, right? So to figure this out, and this was the approach that you took before, I would say, I don't know how I would make this into a graph because it's like, how do I represent each half of a node? How do I represent half of a node?
well, could you compare your illustration before you get caught up in that? What's, you sort of blacked out the top of that triangle. What are they blocked out?
They blocked out. What do you mean? I'm confused.
Or maybe I think that you said, how do you represent half of the grid?
Yeah,
Why do you need to represent half?
well, because it can't go on here. So like this is all gone. The car cannot travel in this space because it cannot go past this diagonal line.
But it's in 0, 0 already. Like that's where it starts.
So it's like have 4 wheels on the wrong side. Sorry, 2 wheels. I
So
guess,
it's at 0, 0, so it can go.
Well,
It
so
can
look,
go there.
I guess look at the illustration they gave you. Look at the illustration.
Oh, I see. So this is not meant to be blocked out. Which one?
Yeah.
2, 3.
There's a very dark one.
Okay. Okay, that's good. So then I can represent everything as moves if I want to. Okay, so if I turn this into a graph, and I'm trying to, is there a different color? I don't get
I only
it.
had like blue one today.
Okay, so since you can go to the right or you can go up, I would do something like I'll draw out the nodes that we have here. Right. Yeah. So the car is right here, and we wanted to go this one. Then I guess we can just.
If I can interrupt for a quick second.
Okay.
You're still making the question harder than it is.
Really?
So before you get, so this is, I think it was because of sort of the earlier time, but this is 0, 0, right?
Yeah.
And the destination, no what the picture is, the destination is what?
Destination is 4, 4.
Okay, so this is 0, 0, this is,
1, 2. No, yeah. I don't know.
well, all right, so we're talking about
I'm
grid stuff.
confused.
So let's just, forget even answering the question. This is 0, 0, what's this?
No, wait,
Zero.
this point is 0, 0, right?
Sure, okay, so that point 0, 0.
Yeah.
I'm gonna, yes, okay, that's 0, 0, so what's this point?
That is gonna be 0, 1.
All right, and then what's this point?
That is 1, 1.
Okay, and now you're relating these points in this graph, right?
Right, oh, that's not right.
So this is 0, 0, this is 0, like, so that x is supposed to represent 0, 0, right?
Yeah,
And so this is,
that's
1, 1.
supposed to be 1, 1. 2, 2. 3, 3. Where's 3, 3?
that is,
Well, this is not. Where's 3?
so,
It's in this here.
no, this one.
Oh.
Up, top one and to the right.
Okay, okay.
I know that it's easier on the graph than I want, or on the grid. So that, it's not immediately easier, but that kind of makes things a little simpler.
Right,
That it's like, okay, going from the bottom left part of the top right.
okay,
You're not kind of going anywhere in the middle, or you'll have to go through it.
okay. So now, oh yeah, now that makes more sense to represent it as points. So I'm just like, wait, what's the question? We have to find a path to get there. So if we do like the depth for search, then we can just find out where it's going.
Do we have to find the shortest path?
Do you mind if I bring up the
Yeah, go ahead. Bring it up.
I'm just gonna slide.
Yeah, yeah, go ahead. Oh, what is? Right, that's so weird. Did the question even say what kind of path you needed? I think it just.
So the question is actually sort of another counting one, where it's how many different routes can we go from 0, 0 to 4, 4?
Mm.
Oh, okay, so it could be like 1, 2, And that would be like 1,
Mm-hmm.
2, 3, like a bunch.
I think so.
Got it.
Which is like a lot of that.
And
Yeah.
I'm sorry, I was double checking something, so I didn't see what you wrote or illustrated. But it
It's
can,
just like 1, 2,
yes, so that's true.
4.
And also, kind of, as an additional constraint for simplification, it can't be done. Like, it can only go north. You either go up or to the left. They can't go, I'm sorry, up or to the right. They can't go to the left. They can't go down.
Yeah.
So for instance, it can't go like, or actually, give me an example of a normal looking path that only can't legally do.
Of a path that it cannot do.
Yes.
Oh, so it can't do this, like, can't go like that. Like, it just can't go straight up on this line.
Oh, that's true.
And it can't go like something like that, like going backwards.
But for a lot of reasons, it can't do that. But yes, it can't go left, like it can't go back.
Yeah, like it can't, I mean, I don't know who would want to do that, but okay. Yeah, so it could just do like this, and go like that, you know.
And
all
the rules are, you cannot go left or down.
No, it cannot.
That is correct.
Those are the only two.
Well, and like, and it can't go that way. It can't go like this.
Okay. Oh, there. Yeah.
Okay. So, looking at this, I would just say, probably recursive, just to make it do like all the, it can do every option for I, like go I and then do all of J.
This problem reminds me of one that we saw in the DSA workshop in the past, which is the stairs count all the possible ways in which you can climb a ladder. I'm not sure count all the possible ways in which you can climb a ladder, knowing that you can climb 1 step at a time or 2 steps.
Yes, that is the
But
question.
this one is just 1 step.
And then this one is,
So we can do like, we can go, what was it, like east, right? East. I don't even know why I'm writing this. This is too confusing for me. I'm like, I don't know how to do it. If I think about it as a graph, I would say, only, what were those called? Only make an edge if, the neighbors are directly next to you, or I don't know, what was the vocabulary? Only if it's, like, for example, east of that, of this part, right?
Yeah, so to be pedantic,
Uh-huh.
you only have edges to your neighbors. So you only, like, to say add an edge to every neighbor sort of doesn't, it's like saying be a neighbor with every neighbor. That's just,
So,
Meaning,
it could
like-
be something like, the edge is gonna be equal to, like this is I, J, then an edge can equal I plus 1, but it has to stop before, because it doesn't equal 0, 1. But it has to stop at 5. Like it can't go over 5.
I may have distracted you, because I think you're more or less on the right track where you have that intuition of, okay, on the grid, you can either go to the point to your right or to the point up.
Right.
so we could have something like in the previous example where we just care about the valid or the neighbors that are of the same kind. In this case, we could think we only care about the neighbors that are like good neighbors, which is they're not diagonal to the current node, and they're not to the right of the current node.
So
And they're not down.
I have to, any neighbor for I has to be, one greater than I, than the previous I. Does that make sense?
So if I can maybe fill in the,
Yeah.
you don't mind it more.
Oh, yeah.
So the first, so a node isn't just I, it has to be an I and a J.
Mm-hmm.
So we can say what, so the question to ask is what are the neighbors of I and J? And so, yeah, we're all, I think, on the same page with the intuition of, we just want, so forget which ones. How many neighbors should a node have? So how many neighbors should this node have? Forget this one.
2.
And like, without, don't worry about the graph, just in English, what are those neighbors?
It's gonna be, 1 up or 1 to the right.
Do we have a quorum? I do we have a quorum. So, this is 0. Or, well, let's do this. So this is 0, 0, 0, 1, this is 0, 0, 2. What are the neighbors of 0, 2?
1, 2.
So 0, 2, its neighbors are 1, 2, which is this, right? And then what's another neighbor?
0, 3.
And that's this one, right? I say very deep. Okay. So this is sort of thing. Yeah, it just means. So here's a weird question for the graph exercise. Let's look at the neighbors of 1, 1, 2. Which neighbors does that know? This one.
That one has 2, 2. And 1, 3.
Okay. So I think sorry, I didn't also ask if we had a quorum, but.
I'm lost currently.
Okay, so this node, 0, 2 has neighbors 1, 2, and 0, 3.
Okay.
And then there's this next exercise, I said, what about the neighbors of 1? This node, 1, 2.
Okay.
Well, it should be 2, 2, 2, and 1, 3.
Cool. Okay.
And maybe what was confusing you, or what's sort of interesting, is that 0, 2 is a neighbor of 1, 2. But 1, 2 is not a neighbor of 0, 2. And that's exactly conveys the intuition that we want, that we can go up, but we can't go down.
Okay.
So the right, but wonderful graph design.
Okay, so now that we've established how these neighbors are gonna work, it's gonna be I plus 1, and J is gonna remain the same, or I is gonna remain the same, and J is gonna change.
Okay.
But only by 1. Okay. So where we can go from here is we can follow this edge case until this edge case. I don't think that's the right word for that.
It's a funny term phrase.
Then we can say that this will stop when I is equal to n minus 1 and j is also equal to n minus 1.
Is that because that's the destination, or
Yeah.
because that's the almost the edge, almost out of balance in the graph? That's the
That's just
destination.
the destination, yeah.
And then the answer is how many ways to arrive in there.
Right, but that's just the part you don't know how to do.
I was thinking maybe, so since we have established how to get the neighbors, we could have all the neighbors for each node. And then, once we have all the neighbors for each node, we can loop over those and see if the list of neighbors includes the destination that we are interested in. And then for those, well, then we can just count how many list of neighbors have the destination, and that will be how many paths there are to get there.
Okay. Yeah, let's do it.
Okay.
So Alejandro said that we should list out all the neighbors. So starting from 0, 0.
Mhm.
Oh, so the function
Mhm.
could be number, or should I just like write it and then worry about
Whatever
this
is most
implementation?
effective for solving the problem. It's my annoying answer.
I'm thinking that like it's kind of incrementing because so you see like the first example we have the neighbors of 0, 2 are 1, 2, and 0, 3. So we went for each neighbor of 0, 2, we want to explore other neighbors. And then now I'm just like a little confused.
But as let's think of a smaller input. Because this is sort of intimidatingly large.
Okay, yeah. All right, so let's go with like just,
Maybe
Nope, how about just,
2? Okay.
so, and how would we describe that input?
So
As
this,
in, this is an input where n equals 5. First one, that's an input where
yeah,
n
this
equals.
is an input where n equals 30.
I think what about an input where n equals 2? So basically it's where
So then it would just be like this.
So that has 2 circles, but here n is 5.
This is 0, 0, and then this is gonna be 0, 1, and 1, 1. So then n equals 2.
Yes.
Okay. Okay, so let's go with that one. Yeah, it's way smaller.
so our destination could be like 1, 1.
Yeah,
Oh, yeah.
So how many paths are there? Forget how many paths are there? Just
there's just one path.
right.
I agree.
So,
So now let's try n equals 3.
okay,
Or
so,
sorry, if I'm driving now.
Yeah,
That this is a very sort of structured input. Like the islands one, like, oh, it could be anywhere. Or the lakes one. Here it's like there's a pattern that I guess like we always know that the neighbors are going to be like this one is.
yeah,
mhm.
And so with a question like that, one of the many millions of tricks we can learn is like, okay, kind of we always want to start with smaller. But there can be a lot, we might notice a lot of structure as we go from n equals 2 to n equals 3. Probably n equals 4 is going to be a bit. Yeah, so this is n equals 3. And so let's just try just counting how many paths.
I think 2. I see 2.
yeah, I think there too.
And could you actually draw the knife just for because it is nerve wracking. It's like, what if we get it wrong? I think it's 2 as well.
So, 1,
Are we noticing any patterns yet?
I did notice that we have the 2 paths intersect in the in 0, 1 and and then 1, 1. It's like kind of in the diagonal.
Oh, yeah.
So that's probably gonna keep happening.
The 1. Yeah, because 0, 0 can't go anywhere besides. Oh, no, wait, it can. It can go to 1.
Also, I would draw the path right at those two. You think there's only one path there? And I think we're right.
Like that.
Okay.
Oh, wait, yeah, so it can only go to 0, 1 because the diagonal line is on 1, 1. So it can't. So, oh, yeah, so this was always gonna happen.
Okay.
But how is that gonna help us? Alejandro?
I have no idea. I feel like so we will have, as the graph gets bigger, we will have
I don't think.
intersections, and then there will be, like if you were drawing, I see if you were drawing the paths, you will see like squares being formed. You see the square that's formed there?
Yeah.
I think as the graph is growing, we will see another square that's bigger. So, and yeah.
I mean,
This-
I like what you were saying earlier about like finding all the neighbors and then just counting how many have the destination in mind.
But I think, with,
But how would, yeah, go ahead.
I think I'm actually interested in seeing this one and 4. So then
Okay,
let's draw the paths for this one.
so this one would, 1, you can go 2, 3, 4. Wait, did I do that one
Yeah,
already?
so that-
No, that's it.
5,
right.
and I think that's it, right? Is it?
I think so. I think seeing another. Yeah, I think that's it, and we can kind of see the same, yes, squares forming. But yeah, I'm not sure how we could use that.
Oh, I think it might be 6. See. Let me draw it over, because now I'm so confused. So, 1, and then 2. Where do I go next? 3.
You already went there.
4.
There's one.
There's one more. Which is
Left, up, left, oh, right, sorry,
right.
right,
Another right? What?
yeah,
All the way down here?
yeah, and then up.
Oh, so there's just 5. Okay. So, oh, let me do this one over so you can see that little. I saw before. I don't know. I see like a lot of squares, yeah. I see that happening, but,
Yeah,
and 5, does it only have 6 paths? Is it? No, I don't see it having paths because n is 2, only 1, n is 3, this one it goes up instead of going down like the other one. Like you see,
This
when
one equals-
n is 2, the path is only 1. When n was 3, the path was only 2. But then now n is 4, and then there's 5 ways.
Oh, and there's more paths than there are.
Yeah.
Oh, that's not crazy like that. For this
Yeah,
sort of
but it's
stuff.
not like a pattern that, we would have to go do more examples to see.
Yes.
What are you thinking, Alejandro?
I feel like I still don't see a pattern, but I do think about like for each node we have 2 options, going up or left or right. I don't know why I'm confused today. But we don't have that option for those that are kind of in the diagonal because we cannot cross that. Yeah, I don't see what the next step could be. Aaron, could you give us a hint or intro?
I think if we start at the end, maybe, but I don't know how we would.
So let's see, we have a little over 5 minutes. So first, just cards on the table. I know what I think. I know that a lot of tools that I know, guys. I'm not sure if I have been thinking. I'm not sure if I can say that. So just like as in, so stuff is tricky. The one like I usually see the answers before I show. If I want me to just sort of share vocabulary, I guess.
Yeah, graphs.
Because I can't say, oh, let's check. So first, yes, I like graphs. And I think that is definitely a way of thinking about, here we're exploring out from like every possible branch sort of thing. There's a very related problem that keeps on distracting me where you don't have this restriction. Where it's just sort of a neat little math equation. And I've been trying to think, is there that way of adapting?
Is this related to the traveling salesman?
No. Sorry for the quick answer, but sorry. And that is a much more intimidating question. I will point out, it's not, and I was trying to think, so, if I were doing this question. This is also blue. Oh, thank you.
Oh.
I do like these ones, so I'm going to, yeah, or we'll actually just take them. More thoughts. But I'll say, this structure is reflected here. Not quite the same way, because for instance, we have this path. So, you say, all the paths that end here are also, like, so we're at least going to have 2 paths in this bigger example. Because we know there are 2 paths here, and then they both have 1 path to new end. But then, we have some amount of paths here and some amount of paths here. And that's what I'm a little, so if I were to follow through this, let's, for you at the very beginning, you were saying about recursion, where it's like, all right, if we have n equals 7, we can think, well, we have the n equals sort of 6 case. Okay. And n equals 7, we think of the previous case, where we had, we only have 5, 5. And we say, well, we have some number of paths to get here, and some number of paths to get here, sorry, let me go. This is the 5. We have n equals 6. 1, 2, 3, 4, 5. And I'm not going to draw the whole thing. I'm saying, well, previously we had n equals, previously, I might say, recursively we had somehow solved n equals 5. Or not solved, but we have useful information that n equals 5. Now let's say we know all the paths that end here. Let's just call that, there's many paths. And let's actually look for them so we know exactly how many paths end here. and there's D many paths. And then here there's C many paths, and here there's D many paths.
Mhm.
How many paths are there for n equals 6?
A plus B plus C plus D.
And then,
So for all the paths that end here. If there's the goal to get,
yeah.
yeah,
So
so
one.
One.
yeah, you can't take any further here. You can go right.
Just one.
You know, I think, well, hold on, now I'm thinking, well, this can still go up.
Oh, but
But-
they.
I'm saying, well, then it would have been a path that ended here.
Mhm.
So that's not double count. That's.
No, it wouldn't in there, because then you can go to the right.
Oh, but what I mean is that when we're considering all the paths for the n equals 5 case.
Oh, for the end,
Yeah.
okay, yeah.
So
Mhm.
what's confusing is that this is not, the answer for n equals 5 is just the paths at the end of the day.
Mhm.
So we can't just say, well, let's take that answer and add 4 to it, or 1. But we also have to kind of do this adaptation where how many paths end here and here, which are like, these are not the ones that we would have counted for n equals 5, so we kind of have to go back.
Mhm.
But either way, yeah, I agree that it's this. So it's a plus b plus c. So in other words, it's sort of that previous one.
Well, at least we know that when n equals 5, there are at least 5 paths. And let's see, how would that work out?
So this is more general, this is a recursive idea, breaking things down.
So it's always going to be.
This is like, hard. I was like trying to do that with the 5. Okay, I think I did it. Is the answer 1, 2, 3, 4? Is the answer 10?
How do you get to 10?
I just like 3 tops.
But those are only 4 paths.
Yeah, I did it with, I started from this one and then it's like, oh, what if paper instead of
I see.
button.
Well, so you're set, so I agree there's 5 paths that end here that then go up. How many paths end here?
We have at least 2. No, 1.
None.
Well, so,
Yeah, just 2.
2 paths and then, so here we have 5 legal paths, and this is the end. But if here is now the end, so sort of bring it a little bit. This by analogy is this. So how many paths can reach this?
5.
Yeah.
Mhm.
So it's in fact sort of like the same 5 paths, which is sort of confusing. But we had 5 that ended here, and went up 1. We had 5 paths that could have further gone, they didn't, and instead they found this new avenue, and these 5 paths went that way. How many paths can be here? 4.
Is that
2. 2. 1.
3 buttons?
Go. And then how many paths can that be?
So the answer to this one will be what we said. Yeah,
So
14.
do we have a quorum?
Yeah. Oh, cool.
So now we still don't have an algorithm. Hey, we're getting something on the equation. Let's try the next one and see if there's a pattern.
Wow. So how many paths, we should just do it on here, how many paths end here? 14 paths end on this one. And how many paths end on this one? 5.
5.
Would that be,
Or let's not be confused, because here, so draw the next column that we're trying. So this was for, yeah, just draw the next line. So then we want to get to the top right.
right, so we can, well, let's use a different color. I know I'm really gonna get confused. So we can start with this bottom one.
Or hold on, so we want to be recursive, so we're saying we now know that there's 14 possible paths here.
Right.
And we have observed that when we're considering this column, we just want to add up how many paths go here and how many paths go. Oh, you know, maybe I confused you.
That will be 15 paths. The one on top.
So
No, sorry. It will be the sum of 14 plus how many paths go underneath.
So how many paths end here?
Same. 14. All the lines cross that now.
Yes, I agree. I think I got mixed up.
So that's 14. And then how many paths on the 100 there?
So how many paths end here?
That's not 15. It's 14 minus 1.
14 minus 1.
No, 14 minus 2. I'm kind of guessing now, because, well, I just know that these 2 lines are not here.
Well,
So I guess by the line we can see.
so we somehow know magically that there are 5 possible paths that end here, 3 possible paths that end here, 3 possible paths that end here, or 1, I'm sorry, that end here.
Okay.
So how many of them reach here?
That'll be 6. No. 6, 7, 8.
Sorry for asking you to draw this right, it was common, it's confusing.
8.
Well, I say that there's only one path here.
But
Oh, but you're going up there.
this,
That was too hard.
There are 5, at least 5. Right.
because all the paths that end here, can go here.
And then plus 3.
All the paths, yeah, they can go one direction and they're stuck, so it's gonna be exactly 3 more paths here,
And then
exactly 1 more path. So 5 plus 3 plus 1 is 9. What about here?
so I'm trying to think that there.
4?
I kind of saw a pattern in the guidelines what it was. Oh,
I would say.
4, yes.
Because this, basically we're sort of chopping off the top one each time. Saying this 5, these paths can't reach here.
Mhm.
So it's all the ones that reach here, it's not 9. So now we subtract 5, we got 4, and we subtract 4, we get 1. Or we subtract 3, we get 1.
Okay. Oh,
And so these are, we can use the sum up for the n equals 7 case. Sure.
Is it? Yes.
Okay.
6.
Or 6. I don't even know. Oh, yeah, no, this is
That's
4, this is 5, this is 6. Yeah. So 42 already.
And then can we do just with 9? Thing? Like 42. Well, the next one will be 42 as well. So you saw the pattern that these kind of repeat 14 and 5.
Yeah,
And then we have
42 minus 14.
oh. But do we really have? Because there's still 14 paths here.
Oh, there was 5
So-
here and then 5 here. So would it be 42 and 42? You saying?
This is interesting.
Who came up with this?
So I do need to hit home.
It's 9 o'clock
It's
already.
9:10.
Oh, wow.
But I just want to illustrate this intuition. Here's how huge you go. You can all have and everything. I say, okay, there's, like, we have this, we're developing this technique where we sum up the previous column and the next one.
Mhm.
So, we kind of get the, what's the term? Prime the pump or whatever is there. There's one path here, there's one path here.
Mhm.
And then we're done. What do I mean by that? What I mean is that that technique we can show, where we say, okay, this is going to be the sum of these two. Right? Because this is trapped going this way. This is trapped going this way. So that's 2. Wait. Am I already confused?
Yeah, that's correct. For an 3 we have 2.
And then
When we have that.
this will also be 2.
Yeah.
Okay, and then this will be 1.
1.
1, yeah.
Or I probably shouldn't go this way yet. But then, okay, so now we have this column filled out. How do we, this is the sum of these numbers, right?
It's 5. Mhm.
This is the sum of these numbers. This is the sum of these numbers. This is the sum of this number.
Mhm.
And then, right, that's kind of, we're getting bored here.
Yeah.
It's an algorithm, we're bored.
But it took a long time to see that pattern.
Yeah. So I'll point out, we don't really, so I like the graph intuition. Doesn't really immediately come up here.
Yeah.
In fact, it's not. What you can think of it is if you look at it sideways, you think here's a tree, and okay, there's 5 possible paths, and they get to this tree and sort of close that. That doesn't really help. Like I said, if you really want to commit to the graph, then I mean, anything helps out. And I think, you know, implementing this in a what's the word? There might be a more efficient way. And to be honest, I bet if you plug in these numbers, I know there's a website mathematicians work on, where you punch in each custom integer sequences, and you get a formula. It's very fast. But you can see, so the initial intuition that this is recursive. So obviously this is not the code, but that's it.
Yeah, I think this is great.
It's like we actually solved it by hand.
That's the experience that I'm hoping.
So I got that off of the printer. Have you used that before? Yeah.
Or can we stop the recording? Not that the million of viewers are going.